Costello from Microsoft, who is one of the researchers at Microsoft. You might notice an Australian accent here. Yes, Craig is Australian, currently living in the US, working for Microsoft. So today Craig's going to talk about isogenies. So if you'd like to share your screen and you can start talking.
Right, let's do this.
Yep, everybody please mute. And if you have a question, you can type it into the chat or you can save your questions for voice at the end of the presentation. Okay, all right, so I'm going to turn off my camera so that Craig gets spotlighted and take it away.
Okay, thanks very much, Joanne. And yeah, thank you all for having me in the seminar series and for the invite to talk. Yeah, always really nice to be able to speak in my native tongue and know that people will follow. So today's talk, it's a talk about finding twin smooth integers for isogeny-based cryptography. Now, Joanne just said that I was going to talk about isogenies, and so therefore I should kind of apologize if anyone came to the talk hoping to learn about isogenies, because that's unfortunately the bit of the talk that I'm going to be giving the least details on. So the aim of this talk is to try to, I guess, in a way, I'm trying to recruit interest in this problem. And part of doing that is, I guess, giving a high level overview of the of what's been done in this direction so far. But to do that, I've kind of got to skip over the details of why this problem is interesting, and just focus on the problem itself. But you'll kind of have to take my word that the problem is interesting and why the problem is interesting in the field of cryptography. But please, if you've got questions throughout the talk, I don't know how easy it is if you'd like to raise your hand or anything like that. Please ask questions, or please save them away and ask them at the end. Or if you're interested in this problem, please feel free to reach out at any time, or just get cracking on it yourself. The point is to try to motivate some interest in this problem, because I've been involved in about 3 or 4 papers that try to look to solve the problem, and I think it's I don't think any of my co-authors will take offense to the fact that I feel like the problem's totally wide open still. There's been some progress made, but maybe you'll agree that none of the solutions to this problem are very satisfactory, at least not mathematically satisfying. And certainly in practice, they don't solve the problem as well as we'd like to solve the problem. So yes, Joanne, if you're interested in the problem, or any of your students are interested in the problem, or if anyone today that's hearing this talk thinks that they might have an idea in this direction, I'd love to talk about it. Otherwise, please go on your merry way and attack the problem yourself. Okay, enough preamble. Let's talk about the problem at hand. So I guess the one slide description of what we're doing in this talk is we're looking for numbers like those 2 black numbers in the middle of the slide. All of the gray numbers either side of those 2 numbers are completely non-interesting for the purposes of this talk. We're just looking for the two numbers, for numbers that are like the 2 numbers in the middle of the slide. The reason being that those 2 numbers are what we call smooth in I guess computational number theory and cryptography. The notion of smoothness is this idea of being divisible by many small prime factors and no large ones. And we make the notion more precise. We'll make the notion more precise in a few slides, but you can see that if we write each of these integers in terms of their prime, their unique prime factorization, all of the integers either side of it have, either side of these 2 numbers have really large prime divisors, which is kind of what you expect on average. Whereas the 2 numbers in the middle, the ones that are in black, the largest prime divisor of the first one is 43, and the largest prime divisor of the second one is 47. So they're what we would call 47 smooth. In other words, neither of them contain a prime factor that's bigger than 47. So if we were to move the smoothness bound down to 40 and say, are these numbers 40 smooth? No, they're not. Are they 50 or 100 smooth? Yes, they are. So that's the notion of what we call B smooth. But these are the types of numbers we're looking for in this work. And it actually turns out that if we fix the smoothness bound at 47, those two numbers are the biggest 47 smooth twins in existence. So we want the two numbers to be consecutive. And it turns out that if you restrict to B equals 47, you won't find any two consecutive numbers bigger than those two, where the largest prime divisor of either or both of them are 47. So if you're going to find any two another way to say that would be any two consecutive numbers larger than these two, will necessarily have a prime factor larger than 47 dividing one or both of them. So they are the largest two 47 smooth twins out there. But that's if you remember nothing else from the talk, that's the problem we're trying to solve. And if you want to have a go yourself, that's the problem that is I'm going to claim that is interesting with applications in state-of-the-art cryptography. But it's kind of nice that it's a problem that's rather easy to describe. We don't need too much technical jargon to describe the problem, but after it's been kind of 3 or 4 years of myself and a few co-authors looking at the problem, and it feels like it's hard to solve in a way that's satisfactory. So that's the purpose of the talk will be to give you a taste of the ideas we've used to solve it or tried to solve it so far. So here's a rough outline of the talk. I have a habit of rambling, but I really do hope to get through all 5 sections. The most disappointing of those 5 sections, I think, is the first one. So as I said, I'm not going to go into the why too much. I've only got 2 or 3 slides on why we're interested in this problem. But if you want to know more information about that, take a look at any of the papers that are linked in this first slide, or please reach out to me if you would like further convincing that this problem is interesting in cryptography. Okay, so why are we interested in this problem? Well, one of the big pushes in the last, I guess it's coming up on a decade now, but certainly the last for more than the last 5 years, is the push for post-quantum cryptography. That is cryptography that we can use on our normal classical Turing machines now, but it's supposed to be cryptography that will be hard to break even in the advent of a quantum computer. So it turns out that at least for the public key algorithms that we use at the moment, in particular algorithms based on the hardness of integer factorization and the hardness of the discrete log problem, or the elliptic curve discrete log problem. So essentially those 3 mathematical problems that modern public key cryptography is founded on, all 3 of those problems become trivially easy to solve if we have at our disposal a large-scale quantum computer. So this whole field of post-quantum cryptography has been a really hot topic in cryptography in the last decade plus, because what we're looking for is new mathematical problems that we can use to replace the existing ones. But these new mathematical problems need to also be very difficult to break with a quantum computer, which factorization and the discrete logarithm problem aren't. So the page that I've highlighted here is the US's National Institute of Standards and Technology, they've been running a competition to try to select the next generation of public key cryptographic algorithms. So this has been running for the last 7 years now, and a scheme that I was involved in that was based on elliptic curve isogenies, that was essentially alive until very recently in the competition, until it was broken, but it advanced to the fourth round of this standardization effort. And there's been a few schemes that have been chosen for standardization already, and there's a few left. But the reason that it's very much still interesting, or that isogenies are very much still of interest, is that I think NIST have called for they've issued a new call for proposals based on the fact that they're not very satisfied, I think, with the digital signature schemes that have been submitted. So in the new call for proposals, they've said, can we submit a whole range of new, or we're opening the door for new submissions of digital signature schemes. And one of the signature schemes that will be submitted is a scheme called SkiSign, that is a scheme called SkiSign that is based on isogenies and whose efficiency depends on the problem that we're looking at in this talk. And so that's kind of the one slide promise that this problem is interesting in practice, because it is kind of foundational to the state of the art in many isogeny-based schemes. So this is an old slide that I've recycled, that hasn't really stood the test of time, because the two schemes that I used to claim that rely on this twin smooth problem for their parameterization, the one on the left B side, which is a key exchange scheme, that has since been broken. But there will be variants, and there are variants of both of these schemes that are still secure and still of interest in the post-quantum community. And these two schemes and their variants, they both require us to define a large prime, and by large I mean at least 200 bits. So we're looking for a prime P that's at least 200 bits, and in both cases, this prime needs to be sandwiched between two composites whose factorization is as smooth as possible. And so the reason why we need this parameterization, that's kind of going to be beyond the scope of the talk. I guess that's key to introducing why the problem is interesting. But you'll just have to take my word that the efficiency of both of these schemes and of future and current variants of these schemes, they depend on how smooth the numbers are either side of that prime. So essentially any large prime will do. We can take any large 256-bit prime, say, but the efficiency of the scheme and whether or not it's practical, it depends on the largest prime, the largest prime divisor of the two composites that lie either side of that prime. And so that's my two-slide very quick introduction as to why this problem is interesting in practice. So here's the kind of one slide summary of the problem or I guess the simplification of the problem for the rest of the talk. So what we're looking for is a large prime P where the product of of P minus 1 and P plus 1 is as smooth as possible. Has where the largest factor dividing P squared minus 1 is as small as possible. So to put that another way, we could say that we're looking for two large twins, M and M plus 1, that are as smooth as possible. And then we could just hope that their sum is a prime, because if M and M plus 1 are both really smooth, then 2M and 2 times M plus 1 will immediately both also be very smooth, and they're the ones that lie either side of this prime 2M plus 1. And so in practice, what we're going to do is we're going to forget about the prime requirement, because it turns out that finding a large, taking random 256-bit numbers, you'll very soon run into a prime number because of the prime number theorem. But finding random numbers of that same size that are very smooth, that's exponentially unlikely. You will almost never run into one just by chance. And the chances of finding two of them next to each other, or two of them that are either side of a prime, that both happen to be very smooth, that's exponentially unlikely. So it'll never happen unless you're doing something a little more clever. So the purpose of this slide is to say forget about all of the connection to the real world, the isogenies. Just take my word that the problem is interesting, if you don't mind, that it's actually got applications to these state-of-the-art isogeny-based schemes. And for the rest of the talk, just think of the problem below. Find two consecutive numbers that whose prime divisors are as small as possible, whose largest prime divisor is as small as possible, and that's the whole problem. And for the practical applications, and for the fact that we need this extra condition of primality, just take my word that that those two things are a lot easier than the problem of finding these two consecutive smooth numbers. Okay, that's the very disappointing part of the talk, which is the why. I hope the rest of the talk will be a little more enlightening. So before we go any further, is there any questions? Any questions? I'll briefly pop over to the chat and see. It looks like some people are having issues seeing the slides. I'm sorry about that, but yeah. Okay, so let's talk about the definition of the definition of twin smooths and this theorem due to Stormer, this ancient theorem that we'll start with. So here's a definition. It's kind of what I was talking about earlier. So we say that an integer is B smooth, with B being an integer, if it has no prime factors that are larger than B. And then quite plainly, we say that two consecutive integers m and n plus 1 are B, we'll call them twins or twin smooths or B smooth twins if their product is B smooth. So if each of them are B smooth, then their product, of course, will be, and vice versa. So that's what we're looking for. We're looking to start with a smoothness bound B, and to find integers as large as we can possibly find that are consecutive, so that they differ by 1, and that are both B smooth. Okay, so our goal is this equivalent goal in yellow here, and we're going to forget about the 2m plus 1 primality condition. So early on, when I first kind of stumbled into this problem by looking at these constructions based on isogenies, I was really hopeful that I could find, two consecutive numbers that are, maybe they're both 3 smooth. So maybe you can find two large consecutive numbers where one of them's a power of 2 maybe, and one of them's a power of 3, that just happen to be next to each other. That was kind of my first and I guess naive wish, was that I could find these things out in the wild. But it turns out, because of this theorem of Stormer, that hope was it was quashed very quickly. The largest consecutive numbers, such that 2 is the biggest prime factor of their product, is 1 and 2. That's as large as we can go. Any two consecutive integers larger than those two will necessarily have a prime factor that's larger than 2. And we can say the same thing for any given smoothness bound B. So the largest 3 smooth twins are 8 and 9. Again, if you look at any two consecutive numbers larger than 9, larger than 8 and 9, then one of them must have a prime divisor bigger than 3. And yeah, if you fix any smoothness bound B, this theorem of Stormer tells you that you can essentially find all pairs of B smooth twins if you solve 2 to the power of pi b Pell equations. I haven't defined pi b and I haven't defined a Pell equation, but pi b is the number of primes up to and including B. So so in the example there, the largest 113 smooth twins, 113 I think is the 30th prime. So pi of 113, or pi of B in that case, is 30. So finding all of the twins with the smoothness bound 113 required, and I did that work early on, required the solution of 2 to the 30 Pell equations. So 2 to the 30 is, yeah, a thousand, about a little over a billion, I think. So solving a billion Pell equations to find the largest such twins, where very quickly, as we increase the smoothness bound, if we're going to find all twins, the number of Pell equations grows exponentially. So it kind of becomes infeasible rather quickly. Unfortunately, more quickly than we would like. So the way that the Pell equation comes up, that x squared minus d times y squared equals 1, that is the fundamental Pell equation. And you can see just by rearranging it, if you put the dy squared over the other side and you move the 1 to the left side, if x minus 1 and x plus 1 are both B smooth, so they're both contain no prime factors larger than B, then they must be a solution of this Pell equation if and only if D and Y are also B smooth. So it's kind of just a way to write down the factorization of x minus 1 times x plus 1 in terms of this integer D that is square free, so it contains no squares of primes. It only contains a product of primes with power 1, and y is y squared is just, yeah, plainly some square, the largest square that divides x minus 1 times x plus 1. So the way that we use Stormer's theorem is, if we try to fix a smoothness bound B, so before we fixed, let's say we fix our smoothness bound to be 113. We don't want any prime factors larger than 113. What we do is we have to search over every possible D who's a product of primes that are smaller than 113 or up to 113 with no power. Well, yeah, you can't have that product D equals the product of the QI. It's either the ith prime is included in the product or it's not. So it's either to the power of 0 or to the power of 1, which is where you get the 2 to the pi of B from. So if you loop over every possible value of D that is a product of those primes smaller than B, you're guaranteed that you've found the full set of B smooth primes. So in that case, again, when B was 100 okay, so I've got a question from Joanne. How old is Stormer's theorem, and how old is the concept of smoothness? The Stormer's theorem, I believe, is over a century old, so it's like the early 1900s. It could even be older. The concept of smoothness goes way back. As I think, yeah, I don't know when it was kind of when it was when things were dubbed smooth and rough, but yeah, looking for things that yeah, I guess it's a bit of a dodgy answer that I said goes way back, but yeah, when the notion of smoothness was introduced, it was certainly at least 100 years ago when the problem of factorization became interesting. But yeah, I'll have to dig up when the notion was introduced. But yeah, they're both kind of rather old. These problems of smoothness and so on have been interesting for at least a century. So yeah, back to this Stormer's theorem. So initially, I was really hopeful that I'd be able to find cryptographically sized solutions to this problem by using Stormer's theorem. But that 2 to the 30 Pell equations, solving those billion Pell equations, I had a little mini cluster of 128 cores that were all running different, all trying to solve different Pell equations, and it took me a few weeks to exhaust that set. And that was for B equals 113, where the largest pair of 113 smooth numbers were both 77 bits. So they're not nowhere near large enough to be used in cryptography. Remember, I said we need numbers that are about 256 bits. And the reason, one of the many reasons that I think the problem is wide open is we have no idea how large B will have to be to hit that 256-bit numbers. We can certainly find them when B is 2 to the 15, so yeah, 32,000 or so. We can readily find, using the methods in this talk, some B smooth numbers, but that number's almost certainly way too big. What we want to do to have a satisfactory solution to the problem is, or an optimal solution to the problem is, find the two consecutive 256-bit numbers that are as smooth as possible, so where B is minimal. That's the idea, and we're nowhere close to doing that in my opinion, which is why I'm trying to recruit interest in the problem. So here's another example. So when you relax B to be 2 to the 22, so that's like 4 million and odd, yeah, more than 4 million. Then you can find solutions to the Pell equation where D only contains factors less than B. There's one of them where we did find a parameterization that can be used, but 2 to the 22 is rather large. So if we go back to the why we're interested in this problem, essentially what that means is, in this case, the largest prime factor looks to be 1.8 million, 1,831,021, that divides P plus 1. In terms of isogeny-based cryptography, that means you have to, if you're going to run a scheme over this parameterization, you're going to have to compute an isogeny that's that large. And computing isogenies that are that large is hard, or at least it takes a lot of time relative to lower degree isogenies. So that's why these schemes slow down when B is big. Okay, so I guess the limits of Stormer's theorem, or at least being able to compute the solution of those exponential number of Pell equations, is why so far there hasn't been an optimal solution. So for the rest of the talk, all I'm going to be doing is kind of giving a taste of the attempts that I've been involved in over the last few years, with initially just on my lonesome, and then once I started to recruit help and interest from outsiders, some I guess progress. We made some progress, but still I'll keep saying that the progress isn't nearly as far as we would have liked. Okay, so here we go. The first attempts at trying to find these large twin smooths. The only kind of bit of, there is a lot of theory that's been developed at looking at the probability that that a given number of a given size is smooth, but not a lot of theory developed when you're looking at two numbers next to each other. So there's a certain number of heuristic assumptions that you can make when you're looking for the two of them next to each other in the wild. But essentially, all of the theory we could take from the literature was kind of is based around, you know, if we're looking at a random number that's at a random number in the interval between 0 and 2 to the 256, which is what we're doing if we're looking for random 256-bit numbers. What's the probability that a random number of that size is 100 smooth, let's say, or 64 smooth, or 2 to the 10 smooth? These sorts of questions relate to this function row of U, which is called the Dickman's row function. So Dickman was someone that was interested in factorization way early on in the early 20th century. And so this notion of smoothness was, yeah, as I said, at least studied that far back. But essentially all we need to know for the rest, or for the next few slides, is so suppose we're looking for a random 256-bit number for which we don't want either of the factors to be larger than 2 to the 128. So if we're talking in terms of bit lengths, you want the largest prime divisor to be no bigger than half the size of the number itself. In that case, you would set U to be 2, and you're looking, and then the probability that a number of that size is 2 to the 128 smooth is given by this Dickman function evaluated at 2. And this is just kind of a table lookup. The way that this function is computed is a whole talk in itself. But the chances of having a 256-bit number that doesn't contain any factors of larger than 2 to the 128, that probability is, or rather, the probability that it factors with no factors bigger than 2 to the 128 is 0.3. So about 30% of the time, you'll have a number, a 256-bit number, where its biggest prime factor is no bigger than half its size, if you're talking in bit lengths. But then, if you increase U, you're decreasing the smoothness bound. So if you want a 256-bit number to contain no prime factors that are a quarter of its length, you set U to be 4, and then that probability drops drastically. So that the chances of finding a number like that is like 4 in 1,000, it looks like, or 5 in 1,000, 1 in 200. 1 in 200 256-bit numbers will be 2 to the 64 smooth. And then by the time you get to the sort of smoothness bounds that we're interested in, like 2 to the 16, this function is becoming exponentially unlikely. And so kind of the point of this slide is we do have a good handle on the probability of a number being smooth. And it's very small in practice. It might take a while for that intuition to sink in. It's certainly not something that was initially intuitive to me, that these smooth numbers are rare, but they are rare. Because on average, things contain, there's a lot of primes that are really large, that occurred before the numbers that you're looking at, and they could all be divisors of the number you're looking at. I don't know if that helps the intuition at all, but there we go. So we're going to use these probabilities to kind of get a feel for how good or bad these kind of naive methods that I thought about early on are. So these are the methods that I kind of looked at or stumbled upon in the early days of trying to solve this problem. Now, the first one, method 1, is this naive method. So if you think about the stuff in green on this slide, that is stuff that we're kind of insisting that is smooth, or that we're inputting that is smooth, and the stuff in red is something that we're kind of hoping turns out to be smooth. So the most naive way to look for these twins would be to just compute products of small prime factors that are 256 bits in size. So I could just take M to be 2 to the 255, let's say. That's a 256-bit number that is too smooth. But the chance that M plus 1 is also smooth even when my smoothness bound here is 2 to the 16. So the chances that M plus 1 just happens to factor with no prime factors bigger than 2 to the 16, that probability is 2 to the negative 70. So that's becoming that's way too small of a probability to be able to even kind of search until you find such an instance. So the second method that helps that probability somewhat is, rather than insisting that all of my rather than forcing M to be fully smooth, what I can do is use the this extended GCD algorithm, or just the reverse Euclidean algorithm, and I can choose, say, I can set A to be something that's around 128 bits, around 2 to the 128, and B to be around 2 to the 128, and I can construct those both as very smooth numbers, and I can choose whichever small primes I like, as long as those A and B are co-prime. And if I then compute the Euclidean algorithm on those on A and B, what it spits out is this S and T, such that A times S plus B times T is 1. That's what you get when you input two coprime numbers into the Euclidean algorithm. And then what I'm hoping for is that S and T are also smooth. And the chances of that happening is 2 to the negative 50. So the intuition there is, rather than hoping for a 256-bit number to be smooth, now I'm hoping for two 128-bit numbers to be smooth, and the chances there are a lot bigger, because you've already cut that 256-bit number in half by insisting that it's a product of kind of two smaller values. So we get a better probability there, but it's still, the probability of these S and T being smooth is 2 to the negative 50, and what that tells me is I'll have to do this Euclidean algorithm 2 to the 50 times until I happen to hit an S and T that is B smooth. So still kind of beyond the realm of something that we could or getting really close to the realm of something that that is intractable, and depending on how much compute we've got. So I guess the first kind of less trivial or less obvious method that I looked at was just taking M, and I've changed it to M and M minus 1, just taking M to be a power of something smaller. So to be, in this case, x to the 6. X to the 6, when I was looking for 256-bit numbers, you're looking for a small power of x, because if the power is too large, then the number of x that you can search over is too small. But if the power is too small, then the factorization that you get with x to the n minus 1, it's not, the factorization isn't really helpful. So in this case, the sweet spot here was like taking the power of 6, so taking m to be x to the 6, and m minus 1 is x to the 6 minus 1. And then what you get is you get this factorization on the right, where you've got like 2 quadratic factors and 2 linear factors, and then on the left you've got the same linear factor x repeated 6 times. So now what you're looking for, if we're searching for m and m minus 1 to be roughly 2 to the 256, then x here is roughly 2 to the 43. So what you're looking for here is you're looking to kind of scan over different values of x in hope that 3 numbers that are roughly 43 bits happen to be smooth, and 2 numbers that are then going to be roughly 86 bits are smooth. And it turns out that the probability of those kind of 5 things happening all together is a lot better than the earlier probabilities. Essentially, the intuition here is the more the more you can kind of cut these factors up and insist that something factors before you go searching, the better the probability that these things are going to be smooth, because the numbers themselves aren't big. And you're ruling out a whole array of prime factors by insisting that that no prime bigger than the, I guess, the bit length that these numbers can take can exist in the factorization. So I'll leave these slides, but in the interest of time, I'll skip forward through the examples of these three methods that were found in the wild. But the best ones I could find where M and M+1 were B smooth were with the smoothness bound B being 2 to the 19. So that second example, X minus 1 factored such that its largest prime factor was smaller than 2 to the 19. We're taking smoothness bounds as powers of 2 just as a rough gauge as to how good the methods are. Obviously, the actual smoothness bound is whatever the largest prime factor is. You can move the smoothness bound to be that. But yeah, so this method found something that was 2 to the 19 smooth, which was, yeah, as good as you could get. On the side of M+1, which is the X to the 6, you could hope for something that was really, really smooth. But on the other side, where you've got these linear and quadratic factors, it's really the quadratic factors that you can see in both examples. Well, actually, not in the second example, but in the first example, it's those quadratic factors, those 86-bit numbers that were letting us down, because the chances of an 86-bit number being 2 to the 20 smooth, it's roughly the Dickman-Rowe function of exponent of u equals 4, which means the probability is small. But again, we don't just need one of these factors to be smooth. We need the combination of all of them to be smooth. And those probabilities kind of multiply heuristically. So yeah, that's why we couldn't find something really awesome with these with this kind of method of choosing M+1 to be an nth power and M-1 to be the factorization there. But that third method gives an intuition into the first kind of really good go we had at the problem, which is this what we're calling the PTE sieve. I've given you the link to the paper in an earlier slide, but this was the first kind of attempt at the problem that we were reasonably satisfied with, but it still doesn't feel like anywhere close to the end game. Okay, so recall in the previous method that the problem was the higher degree terms. So X to the 6. The chances of finding a number that's roughly 43 bits. So finding X to be B smooth is we've got quite a good probability there. And X minus 1 and X+1, those first two factors, they're also about 43 bits in size. So hoping to find numbers of that size that are B smooth is those probabilities are rather high. But it was those two quadratic factors, X squared minus X+1 and X squared plus X+1. If you're plugging in random values of X and looking and just hoping that those numbers are B smooth, it is the quadratic factors that kill you, because they're twice as big as those linear factors. So again, yeah, it's the probability that X is smooth was like 4%, somewhere between 4 and 5%. But the probability that quadratic is smooth is like, what is it? 1 in a million. So that's where we really run into trouble. So the idea in this PTE sieve is, can we find polynomial parameterizations? So can we find two polynomials, f of x and g of x, where f of x and g of x split completely into linear factors? So if we look at the above method 3, that naive method, and we take the power of n to be 2, we get f of x is x squared and g of x is x+1 times x minus 1. That's exactly what we're looking for. We're looking for something where f of x and g of x both split into linear factors. Their difference their difference is, in this case, 1. So the polynomials differ by 1. But the problem here is the degree is not large enough. The n here is only 2, which means we're sieving for 128-bit numbers, where we'd like n to be a bit larger, so we can sieve for a lot of smoothness amongst a lot smaller bit size numbers. So here's an example of such a case where that does happen, where we do have 2 polynomials, f and g. F of x is written as such. It's a product of 4 linear factors. G of x is a product of 4 linear factors. And if you expand them out, you can see that all of their terms are the same except for the constant term. Here, the constant term on the left is 180, and the constant term on the right is actually 0. There is no constant term. So these 2 polynomials, f of x and g of x, they split completely, and the other requirement that we need is that they differ by a constant. And the reason we need that is so that we can divide both of the polynomials through by that constant, in this case 180. And then we're guaranteed that when these polynomials evaluate to be integers, or integers that are multiples of 180, that their difference will be an integer that differs by 1. So the kind of problem that we're trying to solve is find 2 polynomials that both completely split into linear factors, such that they differ by a constant, or such that when you expand them, their constant is different. Again, this was a problem that when we first started to look for these polynomials, my intuition was, these things we should be able to construct these in general. They should be everywhere. It shouldn't be too hard. But very quickly, trying to do these things, trying to construct them, I guess, symbolically in Maple or your favorite computer algebra package, you find out that this restriction is very restrictive. You can always find 2 polynomials that differ by a constant trivially, but the chances that they split into linear factors is small. And conversely, you can always write down 2 polynomials that are split into linear factors, but chances are that they differ just in their constant term is quite low. But in any case, once we do have such polynomials, then we're looking, instead of looking for before, as we were looking for like one 256-bit number to be B smooth. Now we're just looking for a bunch of 64-bit numbers to be B smooth, which the probability of finding those is a lot higher. So yeah, that's what we're looking to do. And it turns out that this problem of finding 2 split polynomials with a constant that differ by a constant factor, it's related to this old problem that's been studied for decades called the Proudhat-Tari-Escott problem. I hadn't heard of this problem before, but apparently it's been studied by mathematicians for a while now. And what you're trying to do is you're trying to find 2 sets of numbers that are the same size. So in this case, the sets are size 4. They've got to be disjoint, so they don't have any numbers in common. Such that if you sum, in this case, if you sum all the numbers in each set, you get the same result. If you sum all the squares of the numbers in each set, you get the same result. And if you sum all the cubes of the numbers in each set, you get the same result. And the reason we've stopped at cubes here is because the set has size 4, and what we need is that their powers up to 4 minus 1 sum to the same thing. And if you've got that, if you satisfy all of those requirements, then you've got a solution to this PTE problem of size 4. And in that case, you've got the polynomials that we need to do this sieving. So I haven't got a pointer. I don't think you can see my mouse hovering here, but basically the elements in the first set become the factors of g of x, and the elements in the second set become the factors of f of x. If you write them as x minus alpha, then alpha ranges over the set of solutions to this problem. And you can kind of prove for yourself, or I'll leave as an exercise for the reader, that if you've got if these things satisfy that, then when you expand the two equations, they must only differ by in the constant term, that all of the higher degree terms must be the same because of this requirement. It's just a lengthy and cumbersome but straightforward thing to convince yourself of that. So that's the problem that we're looking for solutions for. Fortunately, we didn't have to go finding solutions to the PTE problem, because a bunch of people had already looked at a bunch of mathematicians had already looked to try to find solutions to this problem. They were already plentiful for us to just take and use. And in the case of us looking for 256-bit twin smooths, it turns out for some reason that the number of solutions with n equals 6, there's a lot of solutions with n equals 6. A separate condition that we need is that constant can't grow too large for a reason that I won't get into. It's just kind of a technicality, but you want to kind of bound the size of the constant that they differ by, because that I guess has an effect on how you search for these twin smooth solutions. But if you've got, so we just went and took a bunch of solutions that had been found earlier. Some of them are parameterized, which is why there's so many of these solutions of size 6, because there's parameterized solutions where you can kind of just plug in integers and get new solutions. But the cool thing was in that paper was that we could search across many different pairs of polynomials f and g. We could search across them kind of simultaneously by running this sieve. And so in the first case, where f of x is that product of 6 distinct linear factors and g of x is a product of 6 distinct linear factors, what we're looking for, we're looking to search over x's that are, in this case, around 2 to the 40, or 2 to the 42 again. X's to be around that size, where all of those factors happen to be smooth. And it turns out that the probability there is 2 to the negative 41. Again, if our smoothness B was 2 to the 16. In some cases where the solution has repeated factors, like x minus 2 all squared or x minus 21 all squared, that helps, because now we are, instead of the top example where we need 12 numbers to be smooth, in the bottom example, we only need 9 numbers to be smooth, and the probability of those numbers all being smooth simultaneously was a little bit better, 2 to the negative 31. Or put another way, that tells us that we have to try 2 to the 31 values of x until we find a given x where f of x and g of x are both smooth. And 2 to the 31 was small enough, a large enough probability that that we're happy to kind of try 2 to the 31 different values of x until we find one where all of those factors are smooth. So that's what we did. And here's an example that we found using 2 of those polynomials. It's using this PTE solution of size 6. So they're the two sets. The two sets that are those two sets are sets of integers where the sum, that all of their sums and the sums of their squares all the way up to the sums of their fifth powers will be equal. That's why we can write those two polynomials f of x and g of x that must differ by this constant 14,400. And we searched over different values of x until we found one, and that one in green is that given value of u in green was such that f of x and g of x are both smooth, and the sum in this case, the sum of their evaluation at u was also a prime, which is what we need going back to the application of isogenies. And so yeah, so there's an example that we found that p in green is the large prime. P plus 1 and p minus 1 both factor into values that are smaller than 2 to the 15. And I think it still stands now today that that's kind of the best that's been done still. Okay, I've got 5 minutes to go. I'm gonna kind of hurry up through this last method, but that is the best we've done. And if you study this problem for a while, it feels, I mean, 2 to the 15 is okay, but it feels like we should be able to do a lot better. It feels like we should be able to get closer to B being 2 to the 10 maybe, where the largest factors are largest prime factors of these numbers are around 1,000. Maybe that's possible, maybe it's not. It's hard to know. Okay, and lastly, I'll just touch on this very recent work I've got into with a bunch of co-authors that are looking at this algorithm called the CHM algorithm, due to Conray, Holmstrom, and McLaughlin from about 10 years ago. It's like a paper. When I was preparing to give a talk on this problem a couple of years ago, I just was looking at Wikipedia and down in the references somewhere. Sorry, I was given a question. What is the size of the prime in this case? Yeah, going back a slide, that P is roughly 2 to the 256. It's either 255 bits or 256 bits. So right around where we want. Anything over 200 bits is interesting, because we need it to be that size for security. Again, I know that I've swept a lot under the rug here, but I kind of have to. Oh, very interesting question there. I'll come back to that in question time. Let me just rush through the CHM algorithm very quickly. The Conray, Holmstrom, McLaughlin algorithm, it goes like this. You start with a set. So you write down your smoothness bound B. You start with the set of integers 1 through to B minus 1. And you just test all pairs in that set. So you take any two numbers in the set, let them be R and S, and you test whether R divided by R plus 1 and S divided by times S plus 1 divided by S, if that happens to be T over T plus 1, so you write that fraction in lowest terms, if that happens to be a number divided by itself plus 1, then you've found a pair of numbers that must be smooth, because all of the numbers in S naught, all of the numbers in up from 1 to B minus 1 are definitely B smooth. And so we kind of let them all be the first numbers in twin smooth pairs. And then what we do is we just test all these pairs, take R and S to be all the pairs in that set. And if it turns out that product is T over T plus 1, then you've found a new pair of twins that are definitely B smooth. And you repeat this until basically you find new numbers when you scan over all the possible, the Cartesian product of the set cross with itself. So here's an example very quickly. When B equals 5, so we write all the integers from 1 through to 4, in this case, in our set. And we just test them using that thing on the previous slide. And in this case, we go from S superscript 0 to S superscript 1 by finding, I guess, 3 new instances. So we find T equals 5, T equals 8, and T equals 15. And we include those as the smaller numbers in our twins in the new set, so S1. And then we do another loop where we again test all possible pairs in that set, and we keep doing that until we stop where we don't find any new twins. And in this case, when our smoothest bound was 5, we've actually found there in that S3 all of the 5 smooth twins. So the largest being 80 and 81. They're the biggest 5 smooth twins, if you remember from earlier on. And this algorithm in general, it finds, for very small smoothness bounds, it finds the full set of smooth twins. As B gets larger, it just misses a few. But in practice, it's a good enough approximation to the exhaustive problem that it's much faster than doing the solutions to the Pell equation. So I've given some information there of why it's a lot better to use the CHM algorithm than Stormer's algorithm. And essentially all we've done in this recent work is is taken the old record that was found with the CHM algorithm, which they were able to run up to smoothness bound 200, and they found 279-bit smooth twins down in the bottom right there. We just took this CHM algorithm and optimized it as much as we possibly could. We pushed it to the limits, where we pushed it to our limits of B equals 547, where we found like 82 million twins. Unfortunately, the largest such pair was still only 122 bits. So we're still only still like half as big as we need. And so in that paper, what we do is we go and substitute them in to kind of pre-existing methods to give somewhat satisfactory solutions, but again, still not really satisfactory. Okay, time's up. I'm a minute over. I'm sorry for running over. Thanks for your patience. I'm happy to answer questions if we do have time for questions, but please reach out to me if you want to talk about this anymore. But as I said, I think there's got to be better methods out there. I don't think the problem's been solved, and I think it's something really fun to work on because it's an easy thing to write down and understand, but it's hard to feel satisfied with the solution. So thanks for listening.
Love number theory. It is part of the fun of number theory is that the problems are often, able to be understood with only year 12 maths, and the solution is just mind-bogglingly difficult. All right, exactly, we have a question. Hein, would you like to turn your microphone on and ask it?
Yes, thanks. Thanks for the talk, Craig. And I'm wondering if multivariate polynomial bring in any advantage compared to the univariate one.
Thanks for the question. I have never thought of it, and it definitely could. Yeah, it's really interesting. You could have solved the problem. That could be the key. I don't know. I
probably the solving the system of equations to make sure the two polynomials are the same except the constant is probably harder to solve. How much harder to solve?
Maybe.
For X
yeah,
and Y.
maybe. Or maybe introducing more variables allows it to be constructed. I wonder why. Yeah, it's a great. Yeah. If you don't look into that, I will, because it's a really good idea. Yeah, I got to say, I've been thinking of this for years, and you've been thinking of it for less than an hour, and that's a good idea. I'm not just saying that. It's I can't see a reason why it won't work. Yeah, we should talk more, or you should talk amongst yourselves more, because I think it's an interesting thing. You could run into something early that's a good reason why it won't be as good as just the polynomial thing. But yeah, it seems like a promising direction. I think any idea at this stage is worth looking at. So thanks. Yeah, great question.
That's great. Yeah, thanks, Greg.
Okay, a question from me. So you described this one prime that you found. Is that the only one? Is like there a single useful solution, and that's as far as you've got?
No, so that was the best one. Okay. So I said earlier on that the smoothness is the really rare bit. So finding these two m and n plus 1 that were both 2 to the 15 smooth, we have to do a lot of sieving, so like a lot of compute time until we find one that's smooth. And then it was what you're doing at the end. So the chances of a 256-bit number being prime, because of the prime number theorem, is like 1 over log of p. So it's like 1 in 256 of these numbers will be prime, roughly. So put another way, what we did was we sieved until we found 256 or roughly that many pairs, and then you can kind of hope that one of them should be prime. So it's definitely not the only one. And yeah, we found many pairs of twins. I think that was like the best one, with where m and n plus 1 were both smooth, and their sum was prime. Yeah, so there was many found with that PTE sieve, but the one that I put on there was, I think, our best one.
Thanks. Michael, would you like to ask a question?
Just a general comment. With regard to the PTE problem, have you heard of the 2 Morse sequence? Because the 2 Morse sequence actually solves that problem, I think, where the sets are in powers of 2. power of two elements. So the 2-more sequence has a relationship to the PTE problem where you can construct the disjoint sets where the sums of the powers are equal. So maybe I want to just want to
up to. Is it up to?
I don't know. Look, again, it's just that I'm not a computational person. All I know, all I'm aware of is that the 2-more sequence has a connection to the PTE problem. That's all I can say.
Interesting. I'll have to have a look because
there's actually an interesting paper that you can look on the internet, which is by an overview of the 2-more sequence by Christopher Williamson.
Okay.
And that's got actually a little application to the PTE problem. Now, whether that is of any relevance to what you're doing, I'm not sure. But that's all. I just thought, just a little observation.
Thanks, Michael. It's I wanted to also say this, but like even new solutions to the PTE problem are interesting because
but the 2-more sequence is quite well known and it has a lot of applications in number theory. So maybe there's just a direction for you to look through. That's all.
Yeah,
just a very general observation. That's all.
Thank you. Thanks. I'll definitely take a look. And if something comes of it, I'll.
The paper's actually called. I've just got up here on my desktop an overview of the 2-more sequence, and in it has a. It's got section 3 as the Prophet-Terry-Escott problem, which is obviously the PTE problem that you were thinking of. So you might just want to just have a look at that just for some ideas. I don't know whether there's.
Thanks very much. If it turns out to be fruitful, I'll come back to you.
But the 2-more sequence is actually quite prolific throughout number theory and all sorts of applications. So I just thought when you mentioned that, I thought, oh look, I remember reading this. So maybe you can want to have a look at that just to maybe see if there's any tie-up. I don't know.
Absolutely. I definitely will. Thank you. Thank you very much.
That's okay. That's all right.
Thanks, Michael. Okay, next we have Jun.
Yeah, this is a very interesting talk. I'm more interested in how to apply the smooth twin, like in Diffie-Hellman or digital signature application. Can you describe a little bit more about the BSIDH, Diffie-Hellman? That's actually the paper written by you, right?
Yes, it is. And I skipped over the humbling part, which is that the scheme's been completely broken. So it's totally insecure for any size parameters you can find. The same thing happened to I guess the scheme that it was built on, which was SIDH, which was the one that was submitted to the NIST government. It advanced all the way to round 4, and then 2 Belgian mathematicians just completely destroyed it last year, which was devastating news for all of us in the isogeny-based community. But the digital signature ski sign, it's alive and well, and there's a big active amount of research in our field going into looking at that scheme because it'll be submitted to the NIST process, and I think it really stands alone as the only post-quantum digital signature scheme where the parameters and the size of the signatures and the size of the signatures is small enough. They're like bytes instead of megabytes or kilobytes. So it's really attractive from that perspective. But again, just like the rest of the field of isogenies, the time taken to do the signatures and the verification is the problem. It's really slow. And the reason it's really slow is because we don't have good solutions to this problem. And so, I'm sorry that I had to kind of skip over the applications of this problem, but I really wanted to like whet your appetite that the problem is interesting. And if you want more, if you'd like more information on the papers to look at where this problem becomes interesting, please just flick me an email and I'll send you a list of stuff to get into.
Okay, thank you for this information. Thank you.
No worries. Thanks for the question.
Okay, next question we have Nazrin.
Yes, hi. Thank you for the great talk. My question was kind of similar to Shuni's question, because since you started explaining, I was trying to think that, okay, once we find this M and M1, I was trying to find that maybe there is a link that how we can use those ones for digital signature or private public key scheme. So I was wondering if you could explain a little bit more that how we can apply this, how we can use this.
Yes. Okay. So it might just take I'm going to type in the chat
Yeah, sure.
I'm going to type a couple of lines in the chat just because I don't have a slide that's kind of prepared to say this. The very first constructions of isogeny-based schemes like SIDH, they were trying to define primes of the form big A times big B minus 1, where A and B are co-prime, because when you're doing key exchange or digital signatures for the security of the protocol, Alice, who computes A isogenies, and Bob, who computes B isogenies, their isogeny degrees have to be co-prime for security reasons I won't get into. But the very first kind of instantiations of isogeny-based cryptography were looking at this, and that's because you need A and B to divide P plus 1 for a reason I won't get into. But basically, to be able to compute the isogenies using rational formulas that are defined over the ground field, so over FP or FP squared, you need the elliptic curves to be divisible by A and B, and the group order of the elliptic curves. And in the supersingular case, the group order is always P plus 1. So that's why it was initially like this. And the B side and ski sign, the observation was it's enough to have A divide P plus 1 and B divide P minus 1. And so in that way, the hope was that you could use primes that are twice as small. And the reason is that so A and B both need to be around 2 to the 256 for security. I realize this answer's kind of, talking and typing in the chat, which means SIDH needs P around 2 to the 512, where B side and ski sign need P around 2 to the 256. So because of the observation that you didn't need A and B to both divide P plus 1, it's enough for one to divide P plus 1 and one to divide P minus 1. The hope was that you could find that you could move the primes down to be half the size that they were and have the same security, which is true. The problem is early on, you could choose A to be 2 to the, let's say 2 to the 256 and B to be 3 to the, let's say 160. Your A and B could literally be powers of 2 and 3, because all you're looking for, I don't know if that gives a prime, by the way, but there will be some power of 2 and 3 that does give a prime.
Okay.
So you could have A to be 2 smooth and B to be 3 smooth, and that's as good as you could hope for. Alice would compute 2 isogenies and Bob's computes 3 isogenies. The trade-off in going down to primes of half the size was that now we need to solve this twin smooth problem to find co-prime isogenies that are as smooth as possible. So it's just a trade-off.
Sure.
But yeah.
Okay. Yeah. Thank you.
Good question.
Thank you very
Thanks.
much.
I'm happy
Thank
to talk more offline, of course, if these answers don't aren't satisfactory. It's kind of there's a lot of jargon in the isogeny literature that you kind of need to step over to understand where it's all coming from. But
yeah. So not
yeah.
kind of I got the view that how it works. Thank you.
Thanks.
All right, well, we might need to leave it there. So thanks, Craig. This has been awesome. I'm wondering, do you want to just type your email address into the chat so that people
yes, indeed.
know how to
It
contact you?
was on the first slide as well, and I'll send the slides to Joanne in case there's any interest in the slides too.
And
but,
obviously there's some published papers, and I linked them in the start of the chat. So if you want to have a look at the published papers to get the more of the exciting details, they're obviously they're published. I mean, you work for a private company, but you do publish some of the best IP. Yes. All right.
Okay.
All right,
Thanks very much for having me.
Clapping emoji and love heart emoji. Thank you very much. It's been great to see you and great to hear about
Good
this.
to see you too. Thanks, and happy to talk again at any time down the track.
Great.
All the best. All right.
Thank you. Bye.
Thanks for having me. Bye.
Bye. All right, we'll have another CCSRI research seminar sometime in April. Look out for the invitation in your calendar, and have a great soggy Wednesday. All right, bye everybody.